Hi everyone, this is vitalmath. Your surname will probably disappear one day. In England and Wales alone, about 200,000 surnames have vanished since 1901. In China, roughly 85% of the population shares just 100 surnames. 1 in 5 people in China shares just one of the 3 last names, Li, Wang, Zhang. But the real surprise is not the statistics. This simple question, will a family name disappear, gave rise to very powerful ideas in probability theory, the so-called Galton-Watson process, and a field of mathematics that we now know as branching processes. The same method also explains epidemics, nuclear chain reactions, genetics, cancer evolution. In the Soviet Union, branching processes were even classified for some time. So what is a branching process? Why can a family name disappear? How did the first mathematicians who studied the question get the answer wrong? And what deep ideas are hiding inside a simple question? As always, here we explore and enjoy the beauty of mathematics in theory and real life. Don't forget to subscribe, leave a comment in the section below, and share your own examples of branching processes. Let's go! How does a surname live? Typically, it passes from father to son. As long as sons keep being born, the surname stays alive. But what happens after a few generations?
Let's have a look at an aristocrat with the grand double last name of Newton-Leibniz. Suppose he has 2 sons. The first son has 1 son, the second son has 3, so in the second generation there are already 4 men with the surname Newton-Leibniz. Sounds like it's going just fine, but then randomness begins to bite. In the next generation, 2 of those 4 have 2 sons each. One has 1 son, and one has no sons at all, only daughters. So in the 4th generation we have 5 people with the surname Newton-Leibniz, still healthy and expanding. But out of those 5, only 2 have sons. And in the next generation, only one of those sons has a son of his own. And suddenly, by the 6th generation, this once proud surname is hanging by a single man. And who knows, one more unlucky generation and the whole name is entirely gone.
And that is the first lesson here. Even a surname that grows for several generations can still vanish completely. When you see this, 2 questions naturally arise. First, what is the probability of having a given number of male descendants in each generation? And what is the probability that the surname eventually disappears forever? Pause for a second. What your intuition is telling you? Those questions sound simple, but they lead straight into one of the most beautiful ideas in probability. So how did mathematicians tackle this problem? As usual, they started by simplifying reality.
Assume that any man may have 0, 1, 2, 3 sons with probabilities P0, P1, P2, P3. For example, probability of having no sons is P0, probability of 1 son is P1, and so on. And let's make 2 reasonable assumptions. First, assume that these probabilities are the same for every man in every generation. And also let's assume that each man's number of sons is independent of the others. Sounds okay, right? So this way we just defined a random variable x, the number of sons of one man. Now let's get back to our Newton-Leibniz family. In generation 0, the founder has 2 sons. We will use a notation with superscript as the generation number, 0 in that case, and subscript as the index of the man in that generation, 1 in this case. In generation 1, those 2 sons have 1 and 3 sons, 2 values, 1 for the first man in the generation and 3 for the second. And so on for all other generations. Now let's define one more quantity, z sub n. This is simply the total number of men in generation n. We start with one founder, z0 equals 1, then z1 equals the number of sons of the previous generation, which is 2, z2 equals 1 plus 3, which is 4, z3 equals 2 plus 2 plus 1 plus 0, which is 5, and so on until we get z6 equal to 0. Do you see the pattern? Each new generation is formed by adding up the sons of everyone in the previous one.
That is the whole mechanism. To get to the next generation Zn plus 1, you sum the sons of all Zn men alive in the current generation. So this is a random process that starts from 1, and then keeps evolving generation by generation. Each generation depends on the previous, each branch can grow, shrink or die. That is the Galton-Watson process. A population evolving in discrete generations, each individual independently producing a random number of offspring according to the same fixed distribution. Now all we need is to simply understand, will this process eventually hit 0? The moment Zn equals 0, the surname is dead forever. This process inspired the creation of the theory of branching processes, but first let's have a look at how it all began.
Mid-19th century, La Belle Époque in France and the rise of Victorian times in Britain. Aristocratic houses were genuinely worried that common surnames would take over and noble lines would vanish. Smiths and Johns were replacing Morgans and Pickles. So this wasn't just a curiosity, it was a social and political question.
But what is interesting, the story didn't begin with Galton. In fact, the process is sometimes called the Galton-Watson Bienaymé process.
The story began earlier, in France, with the mathematician Irénée Jules Bienaymé. In 1845 he studied the extinction of family lines and remarkably already understood the key fact: everything depends on the average number of male descendants. If the average is too small, extinction is certain. If it's large enough, survival becomes possible.
But Bienamé's work went unnoticed. His original paper was apparently never recovered and results completely forgotten. 30 years later, the question resurfaced in Britain.
In 1873, Francis Galton, a brilliant statistician, a geographer, a psychologist, a cousin of Charles Darwin, one of the founders of eugenics and pioneer of the fingerprints, published Problem 4001 in the Educational Times. He asked two deceptively simple questions. What proportion of the surnames will have become extinct after a given number of generations? And how many instances there will be of the same surname being held by a given number of people? Or, saying simply, when will your surname disappear? Galton received no satisfactory answer, so he turned to his friend, the mathematician and clergyman, Henry William Watson. Together, a year later, Galton-Watson published their famous paper on the probability of the extinction of families. They built a good mathematical model of the process, they wrote down the right equation, and even calculated the probability of extinction, but they got the final answer wrong. They concluded that all surnames must eventually disappear.
That sounds plausible, but it is false. What's interesting, that is exactly the point Bienaymé had understood decades earlier, but Watson missed. Still, this was enough. A new branch of probability theory was born, and I guess you're already asking yourself, but when does the surname have a chance to live forever? Now we can finally answer the central question. Remember, we have a random family tree. In generation n, the number of men carrying the surname is Zn. So what we want to know is simple to state, but hard to answer. What is the probability that eventually this process hits zero? Because the moment Zn equals 0, the surname is dead forever. But the key to the puzzle is simple. There is just one single thing that is extremely important: the average number of sons per man.
Let's call that number m, the mean of the offspring distribution. It is the expected value of x, the number of sons one man has. And with that single number, the whole process splits into three completely different worlds. If the average number of sons is less than 1, extinction is certain. The surname dies out with probability 1. That part feels intuitive. On average, each generation is smaller than the one before it, so eventually everything collapses. If the average number of sons is greater than 1, extinction is no longer certain. The surname can still disappear, but now there is also a genuine chance that it stays forever.
And that is already a little surprising. Even when the average number of sons is greater than 1, survival is not guaranteed. The surname can still die out just through bad luck in the first few generations. But the strangest case is the boundary between the two. When the average number of sons equals 1, a population that on average exactly replaces itself. What should happen then? Maybe a 50-50 case, maybe a perfectly stable state, but the intuition is wrong. Under the standard assumptions, if average equals 1, extinction is still certain. A surname that replaces itself perfectly, on average, still dies out with probability 1. That is a deep and counterintuitive fact in elementary probability. Why? Because average is not the same as guaranteed. Random fluctuations accumulate. Some branches die early, some survive longer, but over an infinite amount of time, the whole line almost surely goes to zero. Fair on average is still doomed to return to zero. At this point you might be thinking, fine, but how do we actually calculate the extinction probability? Fair enough, and this is where mathematicians become really creative. Instead of solving the probability problem directly, they translate it into a different language. A language where the problem becomes easier. And that is the language of generating functions.
If the offspring probabilities are P0, P1, P2, let's package them into one infinite power series by multiplying probabilities by a corresponding power of s. P0, P1s, P2s squared, and so on. That may look like a random trick, but it is an incredibly powerful tool. Why? Because power series come with centuries of knowledge about algebra and analysis, and we know how to work with them.
Instead of dealing with messy sequences of probabilities, it's easier to compress the whole thing into one object and let the object do the work, from probabilities to mathematical analysis. Isn't it smart? And now, here comes the key step. Bear with me, we're almost there.
Let's call g of s the generating function of our probability distribution. And g with index n of s is the generating function for the population in generation n. Then these generating functions satisfy a beautiful recursion. You can simply see this from the definition of the generating function. The distribution of each generation is derived by applying the same generating function to the generating function of the previous generation. In other words, you keep plugging the function into itself. The extinction probability in generation n is given by the value of that generation's generating function at 0, because it corresponds to the first term in the series. So the extinction probabilities themselves also satisfy the recursion. And as we go further and further into the future, the sequence of these extinction probabilities is increasing, and at the same time stays bounded by 1. The third converges to a limit q, exactly the number we're looking for, the probability of ultimate extinction. And in the limit, the recursion becomes one of the most beautiful equations in the whole story. The extinction probability q is the value of the generating function evaluated at q itself. That's it. The extinction probability is a solution to that equation and a fixed point of the generating function. And this is exactly where Watson made his famous mistake. He saw that q equals 1 is a solution, because of course g of 1 is 1, it's the sum of all probabilities, and stopped there. But actually there is another solution, not always, but in the case where the average number of suns is greater than 1. Because the numbers qn increase generation after generation, extinction probabilities move upwards from below and converge to the first fixed points they meet, which is the smallest fixed point in the interval 0 to 1. That is exactly what Watson missed. That's why the boundary value m equals 1 matters. If it's less than 1 or equals 1, the only fixed point is 1, extinction is certain. If m is more than 1, there is a new fixed point below 1, and survival becomes possible with non-zero probability.
The beauty of this toolkit with generating functions is that it is universal. Once you know the offspring distribution, the recipe is always the same. Build its generating function, then solve the fixed point equation, q equals g of q.
For example, suppose each man can have 0, 1, 2, 3, 4 or 5 sons, all with equal probability. Then the extinction probability comes out to about 21%. So even in a population that can grow quite a lot, total extinction is still very real. Or take a Poisson distribution, one of the most important distributions in probability. It is the standard model for counting random events, like how many calls arrive, how many mutations appear, or how many people once infected pass a virus to others, on average. For a Poisson distribution with parameter lambda, the generating function is well known, and the extinction equation is easy to derive. Here lambda is the average number of events per unit, in our story the average number of suns. If parameter lambda is less or equal to 1, extinction is certain. If lambda is more than 1, survival becomes possible. But possible doesn't mean guaranteed. For example, when lambda equals 1.2, the extinction probability is about 69%. And if lambda equals 2, extinction probability is about 20%. Think about that. Even with an average of 2 suns per man, there is still roughly a 1 in 5 chance that the whole surname line dies out. And this wasn't just an abstract toy model. Alfred Lotka, one of the founders of mathematical demography, brought branching theory to real demographic data in the United States. In 1930s, working with data on the US population, he used the generating function framework to estimate family extinction probabilities. His conclusion was striking. For a single male line, extinction could still be quite likely even in a growing population. Based on real data, he estimated extinction probability at about 82%.
But let's be honest, the Galton-Watson process is a beautiful model, but it is still just a model. It is excellent at capturing one specific mechanism – random extinction in a male family line. And that is why it explains, at least qualitatively, why some surnames spread and others vanish. But it is not a forecasting machine for real-world surnames. Real surnames do not evolve only by male line reproduction. People change names, families migrate, spelling merge, women might keep surnames, different cultures follow different naming rules. And in places like China, the dominance of a few surnames is not just a matter of random extinction. Historical assimilation and surname adoption mattered too. So the bad news is, the model is too simple to describe all of reality, but the good news is much better. This simple model was the beginning of an entire field, the theory of branching processes. By the middle of the 20th century, the idea of describing generation evolution with probabilities had grown far beyond surnames.
In the Soviet Union, Andrei Kolmogorov turned it into a broader theory and in the late 1940s introduced the term branching process. Soon after, together with his student Dmitriev, he helped lay the foundations of multi-type branching processes. But then the story took an interesting turn. Parts of this research were reportedly treated as classified.
That sounds bizarre. How do you classify probability theory? But the reason was simple. These same equations could describe nuclear chain reactions. And in the 1940s that meant atomic weapons. Boris Sevastyanov, one of Kolmogorov's students, had classified chapters in his dissertation for several years because of their nuclear relevance. So mathematics that began with family names had become critical for one of the most dangerous technologies in history. But once mathematicians saw how powerful the basic idea was, they started generalizing it. The original Galton-Watson model is very simple. Discrete generations, identical reproduction rules, no lifetimes, no types, no spatial movement, real populations are messier than that. So mathematicians began removing those simplifications one by one.
Some models introduced different types of individuals, each with its own reproduction rules. Some allowed random lifetimes, others allowed individuals to reproduce repeatedly during life. The Bellman-Harris, Sevastyanov and Crumpmore-Jagger's processes are all part of that progression. Later came even richer models: continuous time branching processes, branching random walks, branching Brownian motion, and eventually measure-valued superprocesses.
The main idea is much simpler. Once you understand branching, you have a language for systems where things reproduce, spread, split and sometimes die out. But why do we need branching processes? Because they describe real things. And the most dramatic application is nuclear physics.
In a fission chain reaction, one neutron can produce several more, and each of those can trigger further fissions. That is a branching process almost in its purest form. The critical threshold of a reactor corresponds to the same mathematical threshold as in the surname problem. Roughly speaking, the boundary between dying out and self-sustaining growth. A second major application is epidemics. At the very beginning of an outbreak, each infected person may infect 0, 1, 2 or more other people. In that phase, the epidemic behaves very much like a branching process. The basic reproduction number R0 plays the role of mean offsprings. If R0 is less than 1, the outbreak dies out. If R0 is more than 1, a major epidemic becomes possible. Not guaranteed, but possible. Then there is genetics. In 1922, Fisher used branching process ideas to study whether a beneficial mutation survives or disappears. Most new mutations, even helpful ones, are lost quickly. Only a few manage to establish a lasting lineage. That is exactly the same logic as surname extinction, just in a different biological form. Cancer evolution follows a similar branching picture. Most mutant cell lines vanish, while a few successful ones expand into major clones.
And beyond physics and biology, branching processes show up in random graphs, queuing theory, algorithms, and other parts of pure mathematics. So yes, all of that began as a question about surnames, but really, it's a theory about reproduction, spread, survival, and extinction in general. Powerful theory with beautiful math and fascinating history. But let's summarize a few things to take away. What are the three things I'd like you to take away from this story? First, the question itself. Will your surname disappear? This simple question led to the birth of Galton-Watson or Galton-Watson Bienaymé process, a simple but powerful tool in probability theory. It gives you the model for evolution of family names, generation by generation. Second, the answer. For the question, will your surname eventually disappear? Galton-Watson gave a positive answer, but there was an error in calculation. In fact, the answer depends on one single number, average number of offsprings. Some estimate the number to be around 80% in real life, but of course the reality is more complex than the model. Finally, the implication. Galton-Watson process was just the beginning. It gave rise to the theory of branching processes that appear in nuclear chain reactions, epidemics, genetics, cancer evolution, and many parts of probability theory itself. A simple question uncovered a universal mathematical structure behind spread, reproduction, survival, and extinction. And that, to me, is the real beauty of mathematics. Starting with something small and simple, mathematics extracts deep structure and ideas that are hiding everywhere. Don't forget to like and subscribe. Your reactions would make possible even more beautiful math. Keep thinking and enjoy the beauty of mathematics. See you next time.